Okay. Welcome everyone. Such an early time for us, but you brought good, beautiful weather. Just a few words of introduction about our speaker today, Chris Stott. He was educated in Somerset, England, and attended the University of Kent. Correct me if anything is...
No, this is very good so far, thank
you. Where he obtained a bachelor's degree with honors in American Studies, Politics and Government. And then he received a diploma from the University of California in San Diego, where he studied the international relations and marine policy at the Scripps Institute of Oceanography over there. And he also holds a master's degree in space studies from the International Space University. Early in his career, he worked in British and American politics as an office manager in the Parliament of the United Kingdom. We will not ask you about Brexit. And as an intern in the US Senate and as political aide on 2 US presidential campaigns. He also served as special projects director with Life Education International, a children's health education and drug prevention program. And he also worked in NGOs at the United Nations. He taught international space law at the University of Houston, Clear Lake, and lectured at the University of Houston Law Center. He was previously director of the international commercialization and sales with Lockheed Martin, space operations, and then came to Lockheed Martin from the Boeing Space and Communications Company in California, and is currently the chairman and CEO of ManSat, a main board director of Odyssey Moon Ltd, and also a honorary representative of the Isle of Man government to the space community. And he has many more titles, but today he will tell us about an ambitious project, very visionary project, and I very much hope that will come to fruition, a project about colonizing the moon.
Thank you, thank you, Director.
Well, thank you very much for having me speak today. Thank you, Director Loeb. Thank you, Professor Fazio, for bringing me here today as well, and for Ali Renault, who've made all of this possible. Can you all hear me? Yeah. Great, thank you. When I get excited about something, I'll start to talk very quickly. And if I do that, please raise your hand, slow me down. All right. And so it really is an honor and a privilege to be with you this morning. Thank you for coming in, and especially this time of year. I know you're very busy. So I'm coming to you this morning because we need your help. We need to understand what you need, because we are hoping to work to put a series of observatories on the lunar surface. But it's one thing to say that, it's another to understand what instruments, what type of experiments, what type of facilities that will make you successful in your work, that will allow us to help you in that work. Now, normally I speak without notes, but today, given the amazing audience here, I want to make sure I get everything right, and we do this properly. So people have been talking about putting observatories on the moon since before the Apollo program, actually since before the Mercury and Gemini programs. Going back to the moon was seen as the reason, not a reason, but the reason to even go to the moon in the first place. And what you're looking at behind me is an old 1970s rendering of what they thought would be happening after the Apollo program, with permanent human settlement there. But so much has happened in the last 50 years. We're now in what we would call the second great renaissance of astronomy and astrophysics. We have access to incredible facilities that are being built, from the giant Magellan to the 30-meter telescope, to the extra-large telescope, the European extra-large telescope, to the great observatories that we've had in orbit. It is in a time of incredible discovery. And I know that you've all been a part of this, and you've all helped direct this. And it's your needs as researchers that drive a lot of what we build. And we even have more coming. I mean, hopefully the James Webb Telescope coming soon. But as an amateur astronomer, I've been a fellow of the Royal Astronomical Society for about 28 years. And I love it. I read my copy of Astronomy and Geophysics diligently every month. I don't always understand everything. And I'm always in awe of what you do, of your understanding, and of what you're able to do if you're given the right tools to succeed. And the one thing that I've done throughout my career is find those tools for people. And that's what we're hoping to do going back to the moon. Now, we started talking about this about 3 years ago, when we started looking at new technologies that were apparent, that we could use to do this. We started talking about this before anyone else was. We thought, we're lunatics. What can we say, And that's the thing. I mean, it is our absolute intent to make this happen. Now, if we make this happen or not, even having this conversation with you helps. And having your feedback really helps. Because we're not going to stop with those incredible telescopes that are being built today. We're not going to stop with the James Webb Telescope. Science doesn't stop. It is waiting for that next giant step. And that next giant step should really be back here. That next giant step in astronomy is to go back to the moon and use it as an observational platform. It really is quite superb. And you've got the ability to observe 24 hours a day, 365 days a year. We have the ability to do observations without atmosphere, without weather. We have an incredibly seismically stable platform. Yes, there are occasional quakes on the moon, but they are 1/100th millionth less than quakes here on Earth in their disturbance to a telescope. It really is quite astounding.
No radio interference.
And thank you, yes, absolutely, and no radio interference. It is a beautiful place to observe from. And it is such a unique opportunity that we thought we need to go back and do this. Now, when we were looking at this, we were thinking, my goodness, how do we do this? It's got to be hundreds of millions, if not billions and billions of dollars. But what we've come to realize is, in the last 2 or 3 years especially, the new technologies that are out there with robotics, additive printing, we call it 3D printing, big data, the ability to control rovers, the communications infrastructure has improved dramatically. So the cost of going back is a fraction of what it once was, especially if you do so with robots. And we are coming up on the 50th anniversary. Actually, next week, week after, the 21st is the 50th anniversary of Apollo 8's launch. So 50 years is a long time since we've been back. I know we went back the last time with Apollo 17. And it's one of those things, we can go to Mars, we can land rovers on Mars, we can drive them around, we can do great science on Mars. And it's almost as if we've forgotten this incredible platform to go back to. A great place for interferometry, for the radio telescopes, for thermal imaging, for the study of gravitational waves, neutrinos, the magnetosphere on the planet. I'll get to that in a second. You can tell I'm speeding up because I'm getting excited. Well, especially when we ran some of the numbers, when we realized it is absolutely possible to do this within a pretty reasonable budget. And again, never forgetting that when von Braun and Kennedy and the others really started looking at what do we do, where do we go, and why do we go, it was astronomy and astrophysics was the reason. And that hasn't changed. So, this is what we want to do today. This is just one of our architectural renderings to give you an idea of what is possible. You see a lovely radio telescope over there based on a C.E.O. You have an interferometry establishment there. You've got an optical, all sorts of things. Those little domes are for the robots. No people. This is something you could build facing Earth, away from Earth, This is something that we could build today. There's nothing we haven't done in space already that we're looking at here. It's just that we've forgotten we can. Everyone is so busy building fleets of satellites, which is quite right to provide broadband to the Earth, and ManSat was supporting that. But everyone has gotten so far in advance in their own fields, they've forgotten to synthesize this, to bring it together. This is absolutely possible. We believe if we can get the right feedback and get the right requirements and understand what is needed, hopefully in about 7 years we could begin to do various parts of this. You know, the idea that we could actually start on the radio telescope. We could actually start on initial optical telescopes, initial 1-meter telescopes, just very small radio observatories, and then grow from there. And I'll gladly share these slides, please, because the more we went into the literature, the more we were... It was my ignorance. I should have known better. We actually went into the literature here in the United States, the National Advisory Council, the National Space Council. We went back to the Royal Society back in London, and there are volumes of incredible studies and papers about what we could and should do on the moon. And none of this has changed. And one thing I noticed reading through this was that it was repetitive. The same great minds in the 1930s, 40s, 50s, 60s, 70s, 80s, 90s, through to our century today, all see the same possibilities. They all see the ability to do this and the benefits of doing it. And quite frankly, I'm astounded that we haven't done it to date, because this so needs to be done. So, interferometry invisible at near infrared wavelengths, 10 kilometers arrays. I don't know, a 10-kilometer array sounds like a big array. Imagine that down here on the planet. Absolutely doable if you could get permission to dig the cable fiber. Same thing up there. We can totally do that. Study of protoplanetary disks, interferometry at sub-millimeter wavelengths, an array of a 1,000th of an arc second, ability to study protostellar nebula, high-energy astrophysics. And thank you, Professor Gornstein, for being here today. That was one of the first papers I actually read, was the X-ray astronomy from the moon. And I was delighted when I was doing my research to see that, because it says Harvard-Smithsonian Center for Astrophysics. I lit up like a Christmas tree. I was like, this is amazing. It was fantastic. Gamma ray facilities from the moon. And it goes on. I mean, I won't read every single one. But it goes from neutrinos, gravimetric waves, infrared, far-side radio astronomy. You're in a beautiful cone of silence from the Earth. It really is quite an astounding place to do radio astronomy from. Even looking back at the Earth, even optical studies, studies of Earth's magnetosphere, studies of the solar wind, it really is a beautiful place to observe from. And the nice thing is you can observe 24 hours a day. The kind of observations you need from the Earth to look at certain solar objects, you need, well, according to the literature, we would have to prove this, but you need seconds as opposed to hours of observing time to get the same type of data. Which means with these things on 24 hours, you can do that to the great degree. You can have whole surveys of the sky. It's superb. It's fascinating what is possible. Throw in modern computing. One of the great things about the moon is it's cold. It's immensely cold. It's incredibly cold in shadow. You can create artificial shadows there. You can use existing craters. You can cool down instruments naturally. You can cool down supercomputers naturally. And with big data today, you can actually start to build some really interesting mapping opportunities. This is one of the ones, I mean, again, credit to Scientific American and actually one of the papers that mentioned Professor Gornstein's X-ray observatories. But the idea being, and I pulled this up because I didn't know this, with the moon being outside of Earth's magnetic fields. I had no idea. I've been studying this most of my life. I had no idea. And that shocked me. I mean, okay, I'm an amateur astronomer, I'm not like yourselves. But the idea being that there is so much work has been done to date that we need to capitalize upon. And the idea being that you could actually have an incredible baseline with orbiting telescopes and Earth-based facilities, with the moon and the Earth rotating with each other. And you think, my goodness, but how would you coordinate all of that? You would need an international data network that could actually pull down terabytes worth of data, store it on, you'd have to create these big buildings full of computers with memory in them, and you'd need some great things called machine learning and algorithms. I mean, oh my goodness, we have the internet. We have huge data storage. We now have the ability to coordinate observatories around the world. All we're then doing is coordinating observatories off the world and on the lunar surface. And incredible baseline observations. And really the ability to take the first proper hard look at our planet from afar. If we think the changes that we saw from the Earthrise photo in Apollo 8 50 years ago that created the whole international environmental movement, that really spurred that on, if we thought that one photograph was pivotal, imagine what you will discover for the human race looking back at our own planet that we had no idea was happening because we've never looked. Every time we have taken a look at the universe with a new instrument or an improved instrument, we have learned something incredible. I don't know about you, but I've been stunned every time we see an ultraviolet image, an infrared image, an X-ray image of the universe. It's like seeing something for the first time. Imagine what we will see of our planet where we live for the first time. Because everything we're doing up there is to help life down here. It's incredibly important. Sir?
So, looking at this image, the moon is not protected from cosmic rays like the Earth is by the magnetic field. So, is there any risk from damage by cosmic rays or the solar wind on the moon to the instruments that will be there? Because the maintenance is not as easy. You can't easily fix it.
Exactly. Very good leading question, and thank you. And yes, there is risk. And then if we have a permanent robotic presence, and then hopefully later a human presence, we'll be able to shield properly, we'll be able to protect it, and hopefully go repair as well. So it's not just land and leave it there, it's there, leave it and grow it, maintain it and look after it. But also, you're quite right, for the cosmic radiation and the solar wind, the moon is outside of this. What a wonderful place to have detectors. What a wonderful place to experiment on that. For the actual impact in the regolith, the high energy physics. And that being out is actually a plus, a negative on a few things, but a plus on the others. It gives us the ability to observe and measure that same effect as well. Yes, sir. Question in the back.
So I'm also wondering, I hope, well, not really familiar with the data transfer, like on Earth is we use ionosphere for some data transfer ability. I'm not sure, there's a satellite network needed to transfer data from the moon because we're talking about a lot of
Yes. No, absolutely. Very good point. How do we get the data back from the moon? And what we would be doing there is, at the first, when we go up, we'll be using radio frequencies. And the beauty is, if we go on an Earth-facing side, probably we've actually narrowed down 2,700 different sites, down to 2 possible sites, based on the morphology, topography, what is known, good maps, and also the soil composition for some other potential uses we have. We're facing the Earth 24 hours a day, so we can use basic radio frequency. But you're right, that needs to be coordinated. It needs to go through the International Telecommunications Union, radio regulations. After that, it's laser. And we'll be repeating what the LADEE mission did, the NASA LADEE mission. They were at one point getting 60 terabytes per second back on the laser, which would be fantastic, because that means we're not causing radio interference. Now, we have to look at various sites to bring that down. And you need ostensibly 4 sites around the planet, because 8 hours acquisition and loss of signal as the moon goes around. So and the Earth will be turned underneath. So 3 sites and a backup, and possibly more as well, to bring that data back. And that's, again, the beauty of it. If we move to laser, we can actually really go high on the data rates, and hopefully even higher at that point, because you have multiple lasers, multiple links. Because we're not talking hemispherical, so I'm getting into the satellite thing. We're not talking hemispherical beams, we're talking not even spot beams, we're talking pencil-like beams of data back. And that would probably always still have to be coordinated with the great observatories around the world to make sure we didn't interfere with their observing as well. A very huge role in coordination to take this great giant leap to put these next giant telescopes up there. And then how would we do this? I mean, it's easy to say, isn't it? It's wonderfully easy for me to say this. Oh, we're just going to go do this. Whew. A lot of engineering and a lot of hard work, but we've been talking to a lot of the experts around the world already. And this is from a company called Maiden Space. Give them good credit. The idea being that we can actually combine modern robotics with additive printing, 3D printing, and actually start to build these structures. These structures are being built on Earth at the moment in test facilities. They are also, Maiden Space have a small printer on the space station. The next printer is going up is outside of the space station. Actually having vacuum helps you in additive printing. But the idea being that we can actually start to print various items. This is obviously done for a satellite in space, where we're going to be, they are going to be making larger space structures in and around the space station for satellite communications. So you're actually looking at combining 3D printing, robotics, existing technology, nothing new. We just have to test it. And here is a model of one thing they put together, which is basically, I want to read this to make sure I get this correct, because for the audience here. So it's basically an antenna, simple in design, consists of dipoles, linear wires, several tens of meters in length, all connected to a receiver capable of listening for low radio frequency bands. Now, it looks like a spider's web. It's supposed to. It's actually spun out of the machine here, down, and it feeds in a little pattern. I don't know if you can see this down on the edge, just down on the bottom there, and it kind of spins itself around. So we know we can do this in zero gravity. What we want to be able to make sure is we can do it in 1/6 gravity on the lunar surface. It's a real step forward. And the interesting thing is, they were doing this for satellite communications, where we're limited by the size of our antennas up at geostationary orbit. The larger the antenna, the more signals we get back. And I was asking them, well, you build these huge dishes and antennas up there? They're like, yes. And you have to fit them in these tiny little launch vehicles and get them into the shroud to get up there? Like, yes. And you can print them now on orbit? They're like, yes. Could you print one on the moon? And they stopped and went, oh, wow. We could do that. I never thought we could. Yeah, but no one's ever asked us to do that. But yes, we could do that. And that's the key change that's happened. All of these people have been busy working in their own fields. And for the first time we're saying, well, could you come together and do this together? The big data, the machine learning, the 3D printing, the robotics. And the answer is yes. And this is the other part of what Lone Star is doing. So the computers and everything else would not be on the surface. We'd have them shielded under many meters of regolith down below. So we're actually looking at working with other partners to robotically construct a settlement, a commercial settlement in the moon in one of the lava tubes. This would come a lot of time after the astronomy. The astronomy is one of those things that we can go and do and build an ecosystem and then start to build things like this. Everything you're seeing, this is the architectural drawings. Everything you're seeing there is built robotically today on the planet. If you go to some of the new construction sites, you'll see the little robots chugging along form molded concrete. And that's what we're looking to do.
What is the lava tube? Can you explain?
Yes, thank you. So whether it was from volcanic action or impacts on the moon, what we're finding is, and the Japanese Space Agency did a radar satellite around the moon, they found thousands, and I mean, they're still counting how many they found, lava tubes. So when you go to Hawaii or you go to Italy and you see the tubes that are created by the bubbles of gas and the lava, given Earth's gravity, they form quite small and they form caves that we can walk through. And you can go to Iceland and you can take tours in Greenland, and they're quite beautiful, they're lovely. On the moon, with the gravity there, with the reduced gravity, those tubes, instead of being the size of this room, they're the size of a football stadium and more. The Japanese, in the northwest hemisphere alone, or the northern hemisphere alone of the moon, they found over 2,700 that are appreciable and noticeable on radar. We think there might be more. A couple are 3 times the size of Manhattan underneath. And quite a few of them have openings to the surface. So the goal is to, as we said, we've narrowed down to Marius Hills and the Sea of Tranquility. And why Tranquility? Is because it's an easy place to land. And that's why the Apollo program went there. It's an easy place to land, relatively. I know people talk about the poles. We're still considering that. I mean, it's a very difficult Hohmann transfer in the engineering and orbital mechanics. But there you have lava tubes that are open to the surface, which means that technically we can go down there with robots, we can see what's there, we can seal them off and start working there. And again, you're talking 24-hour-day construction. It's quite revolutionary. It's fascinating. And that's a whole engineering leap in itself. That's probably 2 more cycles of Moore's law, an exponential computing power growth to make that happen. But today we have rovers walking around Mars, well, driving around Mars, not walking, sorry, driving around Mars. We've done that for over 20 years now. 1.4 second light gap, we can do it on the moon too, with those discoveries as well. So this is a phased approach of where you are the tip of the spear. You're the vanguard for the entire human race. I mean, you do that daily. You look out into the heavens every day and you see things that are mind-blowing and change physics. They change everything, our understanding of life itself. But you're also on the tip of the spear for everything the human race needs to do. Because if we are to successfully go out to space, if we are to successfully settle space, humanity needs new energy, carbon-free, we need new resources and new ideas. And astronomy has always been there. And it always will be there. It is so important to what we're doing. Sorry, just one more exhibit. I did ask for one with more water in it. They're trying to put that together at the moment. I said, put a lake in. Where do we get the water from? Well, actually, if you crush down lunar rock, you get water. And silica, and all sorts of amazing things, and aluminum. It's amazing. Yeah, a lot of hard work. We're doing it here, we just have to learn how to do it there. And I know we've learned from Hubble and the others that we can do remote operation in space. But I don't know, I'm hoping one day I live long enough to actually go there and look through a telescope. That's my goal. It's very self-serving. But we're not talking anything truly new. This is from Apollo 16. An ultraviolet astronomy telescope was taken and put on the moon by John Young and Charlie Duke. And that's what it was able to see. It's almost 50 years ago. So we've been there, we've kind of done that. But think how much better we could do it. And there's Dr. George Carruthers on the right, putting it all together. I mean, again, astronomy at the vanguard. A telescope on the moon. It works. So we know you can see some pretty cool things. And this is happening again as we speak. Now, forgive my pronunciation, the Chang'e mission. Chang'e 3 carried a UV telescope. Chang'e 4, which launched last Friday actually, on the 7th. Chang'e 4, which is heading to the Aitken Basin on the lunar far side. And I looked at their mission objectives, which are public domain. And there's obviously geology they're looking at on the Aitken Basin, but also carrying out low-frequency radio astronomy, carrying out solar coronal observations, and studying cosmic rays. So, look at that. There's an observatory on the moon. We're about to land on the moon, I should say, for Chang'e 4. So all we're doing is taking that the next level up. We're taking that, using the 3D printing and the robotics, to what more can we build there? How can we work and do a step forward from the Chinese? It'd be fantastic. The Israelis are going in February with the Space IL mission. I believe India's heading back too. There's a large NASA and National Science Foundation effort at the moment looking at where do we go next? How do we go back to the moon? Now, we're looking to do this commercially. So we're looking to do it efficiently, fast. But part of what we're looking to do is put those facilities on the lunar surface. That could actually be a boon to astronomy. As an astronomer myself, I am slightly partial to doing that. It's also the great logical thing to do. So why not? Why not take that next giant leap? Why not push science just that little extra bit forward? Yes, those incredible telescopes are being built down here, and we will work with them and leverage their studies and findings. But it doesn't stop. And it's only fitting that someone like Harvard, the Harvard Smithsonian Center for Astrophysics, should be a part of this. It always has been a part of this. It's a natural step forward. So one day, soon, if we do it properly, this would be in less than 10 years from now. If we do it properly, about 7 years from now for the first instruments. Yes, sir?
Can you mention the order of magnitude of the cost?
Of course. Absolutely. So something like this, again, depending on what the requirements are, Getting it there is about $100 million. So the cost of the experiment itself, I imagine the same payload, if you match that into a geostationary satellite equivalent, you're looking at about $150 to $200 million. But if you're looking at what can we do there with robotics and in situ resources, it isn't packing up a huge radio array or a telescope itself and setting it down on the moon. It's what can we take with us, what bare minimum do we take with us, and what can we build there around it. It might not look as elegant as this. It might be coated in regolith, it might be made out of lunar concrete, but it'll work, and it'll be incredible, and we'll keep building out from there. So I would say probably, I'm hedging, aren't I? So my subconscious is wiring away. You're probably looking at something like that for about $250 million. Exactly. Yeah. Oh no, $250 million for the first telescopes to go there, either for the first radio astronomy facility or for the first optical. But once it's there, once we know what to take, every mission that goes backwards and forwards after that can bring more and more and more. And those robots can keep constructing 24 hours a day. Yes, when lunar night happens, the idea is the first thing they build when they go up there is one of these shelters. You know, we're not too sure how to keep them going over the lunar night. There's lots of studies looking at that at the moment. It gets very dark and cold. Great observing, not so great for the power packs from the poor robots that are out there trying to build things. But that's okay, that's downtime. So it's a step by step. It's almost like a seed you drop onto the surface that grows and grows and grows with requirements and control from down here. It's fascinating. I'm hoping the best thing we can do is to really take the next step and go back. Because I don't think anyone else is thinking that big. And you guys look at big every day. You're kind of almost used to it. I mean, you look at the whole universe. It's incredible. And so what we're saying for the astronomy community, for the space community, is think big again. Boot, don't spatter. Go back and do this and make it happen. And that's why we came to talk to you today. And happy to answer any questions. Happy to keep chatting. And thank you very much.
Maybe I'll just ask the first question.
Please.
Can you elaborate on the current status of this vision?
Yes.
And who is interested and other funders that are potentially willing to take this step?
Well, and then also understanding I'm under a fair amount of non-disclosures, and I am on camera.
Okay,
whatever you can tell. So I can tell you that we have basic letters of intent in place with the launch providers, people who have said, yes, we can get you there, which is a great first step. And so there we're leveraging the investments of others and the technological advances in the launch industry. On the potential funding side, on the other technical side, we've actually been having meetings with other technical providers of the robotics and the 3D printing. I'll be heading out to the West Coast for some more meetings after this meeting, and we're actually in DC for some more meetings on this as well, looking at the sort of subsurface on the research and development. So it's early days. The initial funding has been done. What you would call pre-Series A, the angel funding, but the founders funding has been done. And then looking forward, we're actually turning to the satellite communications industry, to the people who fund that $300 billion a year marketplace, and saying, right, the same way we fund a satellite, how do we fund something like this? And start with a blank sheet of paper. And so we're looking at everything from, there'll be a next round, then there'll be debt and equity, there'll be an IPO, and others.
But politically speaking, you're optimistic.
Very. Very optimistic.
The government is not part of this, or
No.
not interested?
Well, no, we haven't asked them yet. And I think there's not a lack of respect at all. And it's understanding that at some point, of course, we'll have conversations. But we wish to do this irrespective of politics. And we think this is the next proper step to build a lunar economy, an Earth lunar economy. And we think it's faster, more efficient to do it privately. And we want this to be an example to the rest of the planet. We want the rest of the world to see that commerce and America can do something like this, and that the rest of the nations of the world can be a part of this. And that in the settlement that I showed you of, we call New Hope. The idea being that we live in an age of technological marvels. I mean, every day it's incredible. You know that. But you walk down the street and everyone is miserable at the moment. The whole planet is like in stunned shock. I'm like going, this is an age of marvels. You should be ecstatic. But by doing this, we want to give the human race we want to give them new hope. We want to give them new energy, new ideas, and new resources, and give them the ability to think beyond themselves, to look up at night and see humans and robots living and working on the moon, and everything we do there is to benefit life down here.
You know, on Sunday we had a workshop here talking about a topic of transferring life between planets and so forth.
Yes.
But someone showed an image of a moon lander that was drawn like 50 years before the Apollo mission. And someone envisioned that kind of a mission. And the only difference from the real mission was that the flag was British rather than so thinking ahead is really...
We must. Yes, sir.
What does international law say about who owns the real estate?
Exactly.
On the moon? And does the nascent Space Force have anything to do with that?
That's a really good question. And one of the first studies that we've done, the first employee at the company, at Lone Star, was our general counsel, who very kindly joined us from one of the world's largest space and satellite law firms as a senior partner there. So the first thing we did was study exactly that. Because if you don't get the regulation correct, it doesn't matter what we want to do. What might be technically possible isn't politically or legally possible. So under the various treaties, you've got the Outer Space Treaty, and liability regulation, astronaut rescue. You have our domestic law here in the United States. And so what we're looking at the moment is this would be an American settlement. It would be under a US law. It would be under various variations of state law underneath. But it would be an American base, as in, Apollo 11 Tranquility, Houston Tranquility Base, the Eagle has landed. Now, under the Outer Space Treaty, we are allowed to have a base on the moon. You don't own the moon. You don't own anything around it. You can't lay sovereign claim to it. No nation can claim it. You do have rights of in situ resource use. So I think the best way to describe that is you land on the moon, you kick over a rock as an Apollo astronaut, it's not yours. You can pick up the rock, but the moment you pick it up and bring it home, it's yours. We're not looking at mining or anything like that ourselves. That's not what we're looking at. But what the laws allow you to do is to have, this called for safe operation of a lunar facility. It has to be open to international inspection, it has to be open to international visit, and it cannot be military. There's a strict prohibition on military activities and military bases on the moon, which is for all nations.
So it's sort of like renting space.
Yes, yeah. I mean, one of the ways we first looked at this, and we did this back in 2000, we've been thinking about this for a long time. We were talking with the UN Office of Outer Space Affairs and the Committee of Peaceful Uses of Outer Space. We said, how do you actually use an analogy to describe extraterrestrial resources? And we gave the analogy. We said, I'm from the Isle of Man originally. We're a fishing nation. So I said, okay, imagine, because space is res nullius, res communis, belongs to all, belongs to none. It's the same as the high seas, and the same legally speaking as the high seas. You have little bubbles of sovereignty with the ships on the high seas, same as ships in satellites in space and orbit and bases. They carry a tiny flag on them when they land. We said, okay, you've got two ships on the high seas. They're in the middle of the ocean. They're over a huge school of fish. Do those ships own the fish? And they go, no, they are the property of all mankind. I said, okay. So, and each ship is flagged to a different nation, and they put their nets in the water. And this is all, we've got it all written out at the UN. And they said, well, do we own the fish then? And they said, nope, those fish are still in the ocean. Nope, common heritage. We said, okay. How about the fish swim into the net? They said, nope. How about we pull the fish into the nets and out onto the boat, onto the deck of the boat? And then the UN paused and said, oh, yes, now you own them. You have to go do something to own it. Not to claim sovereignty, but to claim use of the resource. And so what it allows, the UN Outer Space Treaty allows us to do, is to claim a base on the moon and claim for safe operations in an exclusion zone. And why would you do that? Because if you've got a telescope and radio astronomy and others, you want to make sure there's no plume impingement. Say that 3 times quickly. Plume impingement. And the same thing with radio signal interference. You can actually have little areas for safety of health and life, and safety of experiments and optical. So I teach space law. It's one of my. I just went off on a tangent, didn't I? I'm really sorry. But that's
That's very helpful.
Along those lines, are you allowed to have? You're allowed to bring any sort of radiation? I'm thinking.
Yes.
You need to power this at some point, especially in the beginning. So nuclear power, some sort of plutonium rod, seems to me like a very logical choice. That's what they're using to power Voyager, for example. But I don't know what the laws say. I mean, how would people feel about bringing
we used, I think, half of the plutonium that was produced, for example, the New Horizon mission used.
Yeah,
significant
right,
chunk.
right.
Yes.
So we don't have a lot left.
But good question, because Chang'e 4 does have, as far as we know from public domain documents, does have a radiothermal source on board to provide heat during the lunar night to protect the electronics and batteries.
So so in principle, you would need something like that, or you need to quickly build some sort of insulation that could keep the instrument from basically being destroyed during the lunar night.
Well, especially the batteries, the power sources. No, you're quite right, Adan, and that's a huge question, because on the robotics, it's the power source, and because for some of the instrumentation, having the cool lunar night would be fantastic. It'll get really very cold. It's wonderful, minus 240 degrees, steady state temperature. But it's the electronics and it's the batteries, the power packs. No, and so a lot of people were talking about going to the South Lunar Pole, the North Lunar Pole, because of the access to the water in the craters, and they've also got sunlight so many hours a day continuous for solar power. And we were thinking about that, but it's very difficult to do. Not that we're not into things that aren't difficult, but we wanted to go somewhere too that would be really good for observational reasons, and that we know we can land safely at. And so maybe future missions will be up to the North and South Pole. I think, the Chinese they're headed there right now to the South Lunar Pole, which is fantastic, to the Aitken Basin on the far side. But yes, protecting the electronics and the batteries is huge. And if we can do what the Chinese have done, and take a radiothermal generator, that would be superb. Same things that powered the missions out to Jupiter and Saturn and others, and the Voyagers. I mean, that's what we need to do. Yeah, solar power will cut it only 2 weeks out of every 4. You get 24 hours a day for 2 weeks of solar power, but then it gets really cold. And if you think your cell phone battery goes bad, the batteries up there will be.
The good news is that the thermal background is very low.
Very, very low. Yes, yes.
Yeah, refrigeration. Any ideas about what would be the best use for astronomy? Comments on that?
Low frequency radio right now.
Do you think that would be the best?
The hydrogen.
I think optical too. I mean, if you don't have an atmosphere, optical seems like it keeps the public happy when you show them pretty optical images.
Well, you can get diffraction limit. So I guess you need a telescope much bigger than a meter to demonstrate you're doing much better.
What about dust rising up and coating the mirrors and things like this? Is that a problem?
I think, and good question. Especially if there's going to be other things happening on the surface around the telescopes.
Stirring all that dust up.
Because you do. You've seen it in the Apollo. You've seen it from the lunar rovers, the electric cars, and you've seen it from the astronauts. You do kick up dust. Luckily, with the 1.6, the dust does come back. And I think what we'd have to be incredibly careful of is to keep any operations away from the telescopes. And when we're building them, is to work with the engineering teams to ensure that the very last thing you ever do is take the cover off the lens. And then very carefully, slowly, which we can do on the moon, super slow, but we can do that back to ensure there's not. But again, with no weather, there's no wind to blow anything on it, which is great. Oh, I'm sorry, you know that. But the idea is being that once they're up and operational, it's like a no-go area. Everyone stays away. That is you keep that as pure environment as you possibly can. And there has been a couple of studies that worry about others mining on the moon. If people start mining so many valleys over or something, could something get kicked up? And it depends what they're doing. But if we do the space law properly, and we're protected by American law that way, and you say, well, how do you enforce law on the moon? Well, you don't. You enforce law down here. And one of the great secrets of operating in space is 100% of the money spent in space isn't. It's spent here. And so when you want to enforce an action, let's say someone is creating a disturbance, they're putting dust up, it's causing a problem, or causing radio frequency interference, you can actually go to them through their governments and through their corporate offices down here on Earth, which is where the real interests lie. And we can actually prosecute down here to keep things safe. But again, if we do it properly with the treaties and everyone respects that, we should be okay. But it's very much on my mind. And there's several studies on people with concerns about that very issue. And I think it's incredibly careful how we build and construct.
You kept referring to the robotic technology.
Yes.
I mean, how close are we to robots being able to do whatever we tell them in a way that is reliable in constructing instruments, constructing observatories?
If we are to believe what the current literature says we can do, we could technically do it today.
So on the ground here on Earth, we can build.
Yes.
There are construction sites with robots now?
Oh, absolutely. Oh, my goodness, yes. If you go for like modern construction, for skyscrapers, for huge developments, for roads, yes, robotics are very much in use. Especially if you go out towards the Southeast Asia and the Far East, Japan especially, massively more so than here. But even here in the United States, there's a rapidly increasing amount of robotics being used. From earth movers to the people doing the ditch digging and everything else to molding and construction, putting cable fibers into conduits and everything else. Very much. One of the things that holds back building antennas with robotics down here on Earth is the size of the structure and gravity. And up there, lunar gravity actually plays in our favor. It allows us to build something quite brittle and quite intricate without having to close it up and stick it into the shroud of a rocket, so it doesn't have to survive launch at 3.5 Gs. And that's always been one. If we build something that beautiful and intricate down here, it's like having a Fabergé egg wrapped in spun sugar and putting it on top of the rocket and hope it makes it. Whereas if we build it up there, we can be as beautiful and as intricate and as artistic in the design and the engineering as we wish. It could be quite stunningly gorgeous.
So this vision potentially replaces humans in space. You don't need humans, you're saying, to do anything. I mean, even for missions that are not going to the moon, you can have robots doing a lot of the tasks.
Well, I would say certainly for surface operations, and I have a natural tendency to protect loved ones. They don't need to be out in the radiation, and they don't need to be out in the micrometeorite environment. The idea of astronauts up there with jackhammers and building things and moving bricks around, it just horrifies me. Because human life is so precious and so unique that there's so much more humans can do in space. They can be living in the settlements, researching science, engineering, and more, as opposed to being out on the surface. Now, going out on the surface for a walk, to see the surface, to experience that, I think would be amazing. It would be incredible. But to have to go work outside every day would be quite terrifying. And I think it's okay for robots to do that, under human guidance and control. So it's humanity and robots, the machines together, finally, as a synthesis. Not a Borg, but working under direction. Yeah, it's safety for everybody. I'll probably get shot for saying that, but... Sorry, sir? From a demonstration, I would say hopefully about 18 months to 2 years. And we would look to demonstrate that on the Earth in as close an environment as we possibly can get. So there's two sites, there's one in Hawaii, one in Iceland, and then also what I would like to do, I spent a fair amount of my life underwater. I would also like to test it down there as well. Because you obviously, not the optical side, but the actual construction side. I mean, they've done a little bit about that on the NEMO missions down in Key West with NASA. But really, I know you've got the currents in the water, but it's more about the gravity situation. Is how do the robots handle that, and how do you build in that situation?
And what do you do when something doesn't work out as planned? You send out the robots, they start walking, they stop.
Exactly. That keeps me awake at night. No, because really, I mean, it's almost as like you have to. It's like anything at NASA. You have to train for how you're going to do this. The harder you train, the easier the task is. So we've got some of the finest minds in the world to tell us how this might fail.
Robots can repair robots, though, right?
Yes, they can. That's the thought. That we can actually 3D print replacement parts. And the nice thing is they're out there, but they're not quite on their own. We've got all of us down here on Earth rooting and working out the crowdsourcing the solutions. But again, with regular missions, going back and going back to fix and fix and fix. And I'm sure we will have failures. There'll be things that will happen that we've never even considered or thought of. But then we'll learn. We won't give up. We learn from the mistake, and we keep going. And that's the hope.
What do you foresee as the timeline? So starting from a demonstration, let's say 2 years from now, how do you see this progressing under the most optimistic scenario? Suppose you get the funding that you need, but what do you see as the...
Most optimistically with the funding, and that'll be based upon successful trials and tests, and which is quite reasonable, of course. Within 2 years, we want to have tests underway where we can visibly create the structures that we need to create, prove that we can do that, even to prove it to ourselves. Because it's one thing to look at this from a technical point of view, another thing to put it into operations. Then hopefully go to what we call bending metal in the space industry, when we start actually to start build and work on that, and have our first launch 7 years from now. And that means that's roughly in the same time frame as an ITU filing as well, because we're going to have to apply for radio frequencies here on the moon.
So 2025.
Yes, sir. Yeah. Oh, I think hopefully for that's it. That's we don't come home. We just stay up there and we keep building. Absolutely. And also we're going to do this open source as well. And so the idea being that any plans that we have, anything that we make happen up there, we share with everybody.
Yeah, so the reason I'm asking is because, you know, the astronomy community is now starting the so-called decadal survey, which is planned for the next decade. And if you're saying that this would be in the middle of the decade, then it should be contemplated. I mean, it should be at least thought about.
Well, thank you. I didn't know that. So this is one of the reasons I came here today to... Absolutely, yes.
Yeah, so that's every 10 years the astronomy community makes a plan for the next decade in terms of instrumentation and missions and so on. So it's good to know.
Well,
this
and
is on the horizon.
no, thank you. Thank you, Director Lope. I mean, that absolutely. I mean, next year is the 50th anniversary of the first human landings on the moon. And again, being personal, I was born in July 1969. I was born that month. And honestly, I thought by now we would be living in a different world. I thought we would have, you know, a base on the moon already. That's what I was led to believe growing up. And I look back in the late 80s, there was a survey about future technology. And they listed the top 5 jobs that they thought people would have in the year 2020. One of which was Lunar Observer. Another one was managing an underwater hotel. But that's what I want us to make it happen. I mean, next year I'm 50. By the time I'm 60, this is it. I want this working. And yes.
Well, one thing you realize as you grow older is that instead of waiting for something to happen, you can actually make it happen.
That's exactly. Yes.
You should also plan to get people out there. I think it actually is very important for people to be able to visit the moon when you have all this infrastructure built. I mean, you get a lot of public support, and of course, public support comes, well, you know, more money to build bigger and grander things. But I think, you know, I mean, I can imagine. I know I would like to. If somebody said, "Oh, you want to take a trip to the moon this weekend?" You know, I would say absolutely. You know, so I mean, of course, but sending a human to the moon is much more difficult than sending robotics. So I think that has to be incorporated in advance.
You've been reading our business plan, Idan, I think.
Well, of course.
No, because you're quite right. Because we have to show that we can go back robotically and build things robotically, and then the robots will then build things for people to go back. Absolutely, yes. Yes. We have to establish that lunar economy backwards and forwards, and that's why science and astronomy is a key element of that.
Yeah. I think really getting the public involved is one of the key things. You know,
Very
get
much.
the public involved, you get the politicians involved, you know, it's all.
Well, the key is really the funding level that is necessary. And if you say it's hundreds of millions and not billions, then it's definitely doable. That's the key.
Yes.
Well, you know, some NASA missions are budgeted at $1 billion.
Sure. So even $1 billion would be, yeah, but this is much more challenging if it's a few billion.
Yeah.
But yes.
So, speaking about the business plan, what's the profits? Astronomy won't.
Oh no, astronomy won't help us do that. But this is science for the sake of science. But what astronomy does, it does help us prove and demonstrate that you can build things robotically on the moon. And hopefully the profit itself comes from the settlement and other elements thereof. And then hopefully with being open source, there are multiple settlements as well. So the idea is, I mean, if we'll hopefully more than break even. We have knock on wood, we all have a good track record of ourselves from actually running successful businesses in space already, coming from the satellite community. It's what we do. What allows me to be here today, actually, which is nice. But we have to make a profit. It has to be self-sustaining. And it has to build an economy. Because otherwise we'll just have a repeat of the Apollo programs, which were amazing, which were incredible. But the moment political support went and funding was pulled, instead of continuing like we should have done, I mean, my goodness, I hope there is a multiverse and out there. There's a version of our world where people actually just kept going and kept, because it would be, imagine what a different world we'd be living in today.
What would be the profit?
I know, but I'm on camera, and this is kind of proprietary stuff. But let's just say the scientific discoveries that we can make up there in bio and genetics and other things, and all the way from having an actual settlement where people live and work and discover new ideas. Like having a Silicon Valley in the moon, where you have an incubator.
The low gravity helps.
Very
Some
much.
industries.
Oh, very much so. Yes.
So we have microgravity on the ISS.
Mm-hmm. No, yeah, but it wasn't built to turn a profit, you see. So, and that's the unique thing there. So the International Space Station today, you have companies like Nanoracks, you have European equivalents, that people are building things to go there and do commercial experimentation, but it wasn't built to be run commercially. Whereas, yeah.
Materials there either, remember?
Yeah.
You have to send everything up there.
Here we go. So, well, the nice thing is,
You can
yeah.
check which industries could benefit from low gravity.
Well, I mean, one thing I can share with you is we were talking with one of the world's largest property developers. And after the shock there was genuine shock when we said we want to go build a commercial settlement in the moon. Genuine shock. And after the person stopped laughing, it was a good 2 minutes of laughter. And that doesn't sound like long unless you're in the room with the person. They just can't stop laughing. And, we've got to think big. And the first question out of their mouth after they were, was, how are you going to pay for all the concrete to go to the moon? It's going to cost you trillions of dollars to take all the concrete up just to build it. And I'm like, but it's made of concrete. And it's all the resources we have up there are needed up there. They're there. And that fundamentally changes some of the economic equations. When you go back and look at Gerard K. O'Neill's work at Princeton, space-based solar power, the idea being that, the Earth, we are in desperate need of new forms of energy. Energy that doesn't deplete our natural resources, that doesn't pollute our atmosphere, that doesn't contribute to climate change. And space-based solar power is one of those. But if we were to build the kind of facilities that we need on Earth, the cost would be in the hundreds of billions or more. And the effort of launching all of that and the effort of taking all of those resources out of some of the most precious parts of our planet actually has the reverse effect of what we're trying to achieve. But we take it from here. Economics are changed. One of the great things about having human settlements in the moon, where scientists can go and do research and development, as opposed to the International Space Station, is the radiation environment is much safer. The physical environment for a human being is much, much, much better. Even just 1/6 gravity fundamentally changes the physiology and the impact of being in space. And you have plumbing. Plumbing is a huge thing. Yeah, no outdoor plumbing. Yeah, there'll be a little outhouse on the thing. That's for the naughty people. But the actual having the ability to actually have running water, actually having the ability to have proper sewage. I know it's an odd thing to talk about, but it makes a fundamental difference to human settlement. And one of the greatest things about living and working on space stations, how do you reclaim the water? How do you keep the station clean? What's happening in the microgravity environment? Yes, it's fantastic for some of the experiments, but can we duplicate those experiments in 1/6 gravity? We believe we can. And we've got to go prove that on the station. And actually, that's one of the events we're having tomorrow in Washington, D.C. at the National Academy of Sciences with the Angiogenesis Foundation and Harvard Med School and MIT and Johns Hopkins and a few others. We've actually got NASA coming up and contributing to that, looking at what research can we do in the moon and what are the unique medical things we can do there. We're hoping that we can actually, I'm off on the real tangent, but you asked the question, if it's okay to just delve a second. So one of the greatest things about spaceflight, human spaceflight, is it is the first time doctors have been paid to look at healthy people. Really, it's astounding. Before this, all the way back that we know of, no one woke up one morning and said, I feel really good today. I'm in peak physical condition. I could run a marathon. I feel fantastic. I've got good nutrition. I know that there's a plague going on at the moment. The Black Death's happening. I'll go see the doctor and tell him, hey, doc, I know you're busy looking after all these sick people, but look at me. Right? It's never happened. But for space flight, sorry? Well, athletes, but never really, it was always, I've got a muscle ache or I'm doing this or something's happening to me. And so with the human spaceflight program, with I guess getting ready for the Mercury and Gemini missions, they went down to the cellular level looking at astronauts. And since then, too, one of the greatest advancements, one of the greatest reasons to put humans in space is those poor people are human guinea pigs. Everything that happens to their body on a cellular level is looked at. And one of the things we're realizing is if we're doing this on the moon or in the moon, you're going to have a group of humans who are very physically fit, they'll be rotated out and everything else, very well monitored, but also their nutrition can really, really be taken a look at. See, at the moment, the food they have up on space station is food that was kind of generated for the space shuttle missions and a little bit for space station especially, but really went back to the calorie intakes of the Mercury and Gemini and Apollo missions. And so you've got a lot of high sugar, high fat, high salt. It's not really the most nutritious stuff for you. So garbage in, garbage out. So if you really want to start studying the human body and disease control and vector control and genetics and genomics and everything else, by having people living in the moon with, where they're doing aquaculture, we're going to be doing, see, it's early in the morning, not too much coffee. But when we're growing on the moon, we're not growing in soil. We'll be growing in the nutrient-rich waters that we take with us. Hydroponics. Thank you. So we're actually going to be able to control that environment for the human body too, and really learn from the human race that way, and from the people who go back upwards and down, which we've been doing on the space station. But living on space station, what we're finding is the effect on the calcium system, the bone systems, the vestibular systems, the optical systems for men, and the radiation environment up there is really pretty awful. And everyone volunteers to go, and same with the Apollo astronauts, but the radiation environment is really pretty extreme. Whereas we can do that in the moon, we can hopefully learn a lot more in a much safer environment. And then you have all the physical things, all the technologies we can look at, things that we can learn from station and take that to the next level in variable gravity, especially in 1/6, and we think about Mars at 1/3, and it's amazing. So today, the astronauts have like a cellular scan done of their entire body. And normally that's given out to medical science, but they've had to stop doing that temporarily because the scans were so good, there was no such thing as anonymity in the scans. You could look at the scan and know exactly who that was because the scans were that good. And that's been one of the greatest things, is actually having these doctors have time too. Have real time and be paid very well to go look at human beings.
But since the robots will do all the work, we have time to examine humans.
Exactly, yes. So there'll be different reasons to go down underneath.
Just in closing,
Yes.
do you have competition?
We hope so. We want the Burger King effect, is what it's called. And that very quickly is, McDonald's had a lawsuit against Burger King. Google all of this, I'm telling you, by the way. And they stopped the lawsuit halfway through because McDonald's would do all this great research about where to go, what to do. And Burger King would go, I'll just go where McDonald's is. So McDonald's was suing them, and they found out, so it's called the Burger King effect, that everywhere there wasn't a Burger King across from McDonald's, McDonald's would make more money. And so we're hoping for the Burger King effect. We want competition. We want more cities in the moon. We want more observatories. We want more science done. We want more flights backwards and forwards. Because one of the great reasons to do this is to get our human race off this planet. And at this particular point in time, using capital to do so, using economics and a commercial effort, we believe is the best way to do so quickly, efficiently, to let it grow, to let people on Earth profit from it, physically profit in ideas, profit in resources, and profit in hope is the hope.
Well, with that note, let's thank Chris for a wonderful talk.
Oh, thank you.
That was recorded, I guess.
I think so, yes.